Okay, so I represent the Department of Computer Science and Engineering at the University of Colorado in Denver here. And my talk will be about the invertible neural networks for time series anomaly detection. There's a lot of busy slides. I highlighted what's most important in gold, so there's an easy way to focus. But long story short, this effort is gonna see how we can apply the invertible neural networks for anomaly detection and construct improved device similar to what the autoencoders do. And we focus on time series data. The image data has been experimented with extensively, but time series is kind of different and new. So that's what the network this paper focuses on. The keywords will be the autoencoder architecture, and then the invertible neural network architecture, and the hypothesis was that that invertible neural network designed to solve inverse problems, which I will describe in a minute, it learns data reconstruction extremely well, and it's a natural candidate for improved anomaly detection solution, which is very much useful in medical diagnostics as well as the industrial diagnostics, especially where the time series data is concerned. Talk about the motivation hypotheses, which I just kind of briefly described. Then we'll go over very quickly over the autoencoders architecture, and then the very intriguing invertible neural network architecture. I hope I spike your interest in that. That is something which is very good in solving inverse problems. And then we will show how we train invertible neural network as an autoencoder, and present experiments and the conclusion at the end. The motivation is simply that the machine learning is playing an increasingly important role in all the diagnostic processes across many domains, such as healthcare, Internet of Things. And it's important to be accurate because we rely on these anomaly detection systems to tell us what's out of order, what's different from what was expected. And the entire field of diagnostics in general leans on it these days. So motivation is just to improve that type of the help us there, and all of them rely on the data reconstruction capability from the compressed representation, and so that's where the neural networks, invertible ones, come in. The hypothesis is, as mentioned, that is an improved network architecture for anomaly detection, since we are working on general time series data, but it turns out that the convolutions, actually, that some transformations which are along the lines of the convolutional neural networks are very helpful with that domain as well. And at the end, we get a granular, accurate, and resilient to noise anomaly detection system. That picture is just a little, high level picture of the invertible neural network, but let me just, we'll talk about it in detail in a minute. So a quick slide about anomaly detection. I think it's very much intuitive. It's basically recognizing whatever does not belong, whatever is away or different from a pattern, something that sticks out, something that we don't expect. So in diagnostics, the key is that we train our systems on the healthy data only, on what looks right, and the network learns to reconstruct the healthy samples because that's what it sees. And then if if it encounters something it has not seen which stands out, it has trouble reconstructing it. It hasn't learned that, so that's how we know that this is something something off and something is different. And there's a class of networks called Autoencoders. This is the unsupervised family of neural networks famous for dimensionality reduction and then reconstructing from it. There's a bottleneck, so we would reduce the dimensionality, we will extract the features to a certain bottleneck and then learn how to reconstruct X to an X, input to input, and see how close we are. And that's the error, that's the whole idea between autoencoders. There are several types of autoencoders developed over the years. The convolutional autoencoder, the idea is the same, it's just that we leverage the convolutional layers here and transformations to arrive at this compressed representation in that what we call this latent space, and then we kind of go back to try to reconstruct the image. This works for images quite well, and actually turns out we can use similar transformations on the time series data as well, as intriguing as it is. And then another type is a variational autoencoder. This is depicted right here. There's a difference then that this is the probabilistic generative model, and it learns the probability density function of our input X. And with that knowledge, it can actually generate new content. It is the whole system. The decoder is fed with the samples following some distribution like Gaussian in such a way that that new content can be generated based on that. That's one of the technologies in all the deep fake type of networks. And then last but not least, and in fact that's the state of the art autoencoder for the sequential data, that's the LSTM model, or the recurrent neural network exemplified by that long short-term memory units here, where because we are dealing with the sequential data, so we leverage that construct to remember that sequence and try to reconstruct it back to X. But the idea is the same everywhere. We arrived at this compressed representation, and then we are trying to decode it from there. And then let me touch base, conceptually, philosophically, on what this is all about. There's a class of problem called inverse problems. These are, it's interesting. These are called ill-posed problems. That's opposite to naturally occurring well-posed problems, where we basically have a cause and effect, and we know what caused what, and there's not there's no ambiguity. If the inverse problem is a problem where the parameters of some phenomenon cannot be directly measured, and they are just calculated based on some observations, and that typically causes issues because there's an inherent ambiguity in this. Multiple phenomena can map to the same result, right? But then how do we go back? There's this ambiguity. The well-posed problems are defined with these three conditions. A solution doesn't exist, is unique, and it's a continuous kind of space from the mathematical function standpoint. So, but this problem is unique, right? So this is not unique because multiple causes can multiple phenomena can result in the same effect. So that's where these invertible neural networks come in. That's a very interesting domain. What happens here, in order to solve this problem, we somehow need to construct this bijective relationship where we can actually map X to Y and then go back, right? So in order to go back, we need that one-to-one relationship. Well, we don't have it. So what we do, we augment Y with the learned latent space, sampling from the latent space Z to compensate for the difference in dimensions between X and Y. Most neural networks compress data, right? So the dimension of the Y is typically smaller in all the classifiers and whatnot, right, as compared to the input. So we compensate for this because the network learns the probability distribution of X, and it can then augment Y with that, sampling from that, and that's how we have this bijective relationship. So it's a fascinating space, in my opinion, and that's what the invertible neural network is based on. This is that simplistic drawing. There's an X, a Y, and the latent space Z, and we are looking for this bijective function F, which can do these transformations. These networks are simultaneously trained forward and in the reverse direction, and that forward learning process uses this, as I mentioned, additional latent output variables to capture the information which otherwise would be lost. So that inverse process is explicit, right? This is also tractable. Most of neural networks are intractable, right? We cannot really go back mathematically to the beginning, but and because of the certain math constructs, which I won't get into it, it's in the paper, but we can achieve that traceability. So that's pretty interesting, because that, again, that can factor into explainability of this entire solution. And because of that, the INN, I'm sorry, has this, I call it an extraordinary capability to reconstruct, the input data from that latent space. So that's why that's an interesting candidate for the anomaly detection as well. And that's a very brief look under the hood into this invertible neural network. So the interesting thing is it's invertible by construction, right? So it's constructed from these little coupling blocks, which look like that. And I'm going to tell you briefly where's the magic. It was first proposed by Dean in 2016 under the cryptic name of real valued non-volume preserving transformations, real NVP. And later on, a lot of generative architectures were based on it. And together with the normalizing flow, that's another part of that equation. But the idea is this: this little coupling block is constructed in such a way that if we go from the bottom up, the input is split into two portions, xy and x2, and then the two transformations are applied to x1. So x1 maps to part of the y directly, right? This is a direct mapping, whereas x2 is calculated based on x1 and some transformations. These two do not have to be invertible. And this is the scaling, and this is the transformation, right? So it's a T for just basic transformation, and or translation, I should say, and S for scaling. So that's what it looks like here, and that's we arrive at the second component of Y. And the interesting thing is that we can go back. If we have y1 and 2, we can actually reconstruct x2 and x1, because we already know what x1 is, right? Because that was a one-to-one mapping here, and then we can just basically apply these transformations in reverse order, and we actually arrive on x2 because these transformations are applied to x1, which we know that's y1, right? So that's a very interesting paradigm. It turns out that those two functions do not have to be invertible by themselves. We don't care because they can be just applied in reverse order, and they could be extremely complex. So in fact, each of them can, for instance, be a CNN, right? So this way we can actually accomplish that invertibility of a very complex and non-trivial problems. Can be complex. And these coupling blocks, each coupling block, right, that's what they look like. A network is constructed with a bunch of them. It's a chain of them. And it has been proven, which is somewhat intuitive, that a chain of these invertible blocks is invertible end-to-end. So the complexity of the entire solution could be as needed as the problem domain calls for. Okay, so now what our proposed solution here for this improved autoencoder is this. We would like to train the invertible neural network as an autoencoder. Now, how do we do this, right? The invertible neural network does not really have a bottleneck because it's a one-to-one. We just accomplish the bijective, right, mapping through construction, through those affine coupling blocks. So now, how do we do it? So what we did, we basically set is this z part of that dimension here was just basically presented as all zeros. This way, we kind of construct that artificial bottleneck, but in such a way that we are not really remembering, explicitly any data in X, because this is all essentially zero. So yeah, I'm putting it here. We are zeroing this latent space. So now extra information is retained. So the learning process is a true learning process and not a memorization of some sort. And this whole chain of offline coupling blocks, there's a whole chain of those. I mentioned these are all, these types of these coupling blocks have to do with this variety of these two functions we saw in the previous diagram, S and T. So if we apply the convolutional functions as one of these coupling functions, you have the convolutional coupling block. Now we can have a fully connected coupling block. We can have reshaping, and because it simply depends on whatever we plug in as those two functions. And again, because of the nature of that equation we saw above, the whole thing is invertible from end to end. For this particular problem, since we experimented with time series data, we actually tried to use the convolutional layers, and we kind of did the 2D transformation of this input. And then we also have the in describing in here this multiplexing wavelets transformation. So the reason is in the time series data, there's a lot of similarity, low-level similarity between those healthy and abnormal samples. So we want to kind of separate them from what truly is different. So we don't want to have the network confused by these low-level similarities. So we kind of split it into these channels, and we focus on the high-level differences, and that seems to be very effective. This whole process leverage something called the framework for easily invertible architecture. that's very helpful because, it seems like it's a complex solution. However, there's a framework called the Framework for Invertible Architectures. There's the link to it, and what it does is basically an abstraction in front of that invertible neural network concept. So easily, by simply there's an SDK in short, right? So we can construct the chain of these various transformations using those APIs, and these blocks, they are higher level blocks, such as GLOW or NICE. These are the names for the specific architecture known for the image reconstruction, like GLOW, for instance, a famous model. So this architecture can it offers the API or the SDK to easily do it. That's why we don't have to really dig into this detail and the intricacy of these functions. We can just configure it on a high level. It's essentially a higher level SDK to this. So that's very helpful. That's what I did to construct this whole network, which you saw above, simply by calling those, by constructing the subnets, quote, quote. So that really helps, because otherwise it will be a very complex idea, more complex, I suppose, than autoencoders. But a tool like this makes it really very quick and efficient. What experiments compare the state-of-the-art LSTM autoencoder, a state-of-the-art for the time series type of data. It compared that with our invertible neural network solution. So that was the goal for the empirical part of this project. And I worked on two data sets. One is ECG data set, and the other one is from the predictive maintenance domain, the vibration data set. It's so let me describe the first one. The first one was 140 dimensions, ECG heartbeat. There was 5,000 electrocardiograms in the data set. The second one, this one, right, as you can imagine, that's the PDM. So we have the vibration sensors. This data set is from the Airbus helicopter accelerometer vibration sensors. It's 61,000 plus dimensions there. So we had to apply some transformations to it in order to make these two kind of comparable. So we don't get lost. So we applied some transformation on that data set. It was reduced to about 240 data points in such a way that each of them is the means of the 256 consecutive values. So now it became comparable with that, and then the ECG data set, the one that was used, is actually a classification data set, which was not our point. Our point is not the classifier, but we kind of massage this data set to become suitable for autoencoder type of architecture. So basically, we kind of simplified it. We labeled all the abnormal rhythm as 1 and normal rhythm as 0 out of these 5 class type of classification formats. So because the point is that we want to train the network only on the healthy data. That data set is just healthy data. They don't provide any abnormal data except for the very small ground truth data set, but this one we kind of adjusted to what we needed it to do. And the methodology was like this. So the INN was constructed. It was described in the previous drawing. There was some wavelet transformations in there, and as well as the convolutional ones. Then as I mentioned, that high dimensional time series input was transformed to reduce the number of dimensions. And then there was the 2D transformations applied to it. And then INN was trained as an autoencoder. You saw the diagram where this artificial bottleneck and all the zeroing that latent space sampling happened there. And then the reconstruction error threshold for healthy samples was captured. And then, the model was the inference. We looked at all that, and we set that threshold at the 95% difference level, right? So if it's higher than that, that's anomaly. And then truth table was constructed, and we repeated this for the various bottleneck sizes of that Z. That's because that bottleneck is artificial to begin with, so it was interesting to see, can we get by without any bottleneck, for instance? And it turns out we actually can. So that is a very busy slide, but just to show you what happened there. So that just shows the dimensions, how through all these multiple layers right here, and then a similar approach was done to this helicopter accelerometer data set. We watch what is the original data, what's the reconstruction data, what's the difference. I know you can see much, but that's kind of visual. You can already tell. I guess it's not our eyesight is not really able to do this very well, but obviously the machine does, so that's why we use machine learning. But and then these were the reconstruction loss, right? So the point is that the reconstruction loss for healthy samples is low, whereas the reconstruction loss for normal samples is high, just like in autoencoders. Then we have a threshold, and that's how we know what is an anomaly. And if this visually here, you see the difference is huge. It's like the order of magnitude difference here. So we also experimented with some toy data sets, basic artificial synthetic data sets. This is the real one. And then, so for the discussion of the results, the truth table, true positive, false negative, right? In these types of applications, it's false negative, which matters, because that is when the anomaly is predicted as a healthy behavior. So that's the red flag. So what we are focused on is not necessarily accuracy, right? We really want to focus on recall, because that measure plays a part in recall. So long story short, that's exactly what we accomplished. If we compare this STLM LSTM autoencoder architecture with INN autoencoder for the ECG and for both data sets, we see that the recall here, the last line here, is significantly better as compared to the classic approach, 70% versus 79%. This is where this false negative piece takes part. So that's what happened here. So with that, we concluded that indeed, given the level of experimentations we did, that this is a viable approach, that the invertible neural network trained as an autoencoder for images previously and then for time series data is a very interesting solution for anomaly detection. It is a complex. One of the I got in the previous conference was, well, it's a complex solution, and it did. So it is in a way, but again, we have this abstraction to create this network through the SDK, and use these APIs, and that's a very quick process. So then just it's a matter of training, and of course the data engineering has to happen no matter what, but the difference, the improvement is significant. So for some mission critical applications, especially in healthcare, right? It is something which might be worth pursuing. So that's all I had. Thank you so much.